All right, let's go and get started. Let me start off. I'll get the sign-in sheet passed around. Just a real quick recap of where we left off. So I started to discuss some of this stuff with you last time, but you all didn't have the slides. So I've got these slides together. This is just the ACI requirements for reinforced concrete beams. And this stuff is really, this applies to just about any element made out of reinforced concrete that undergoes bending. So these requirements will apply across the board. 2, 3, 4, 5, 6, 7. Let's see. Okay, there's that. More. Extras and whatnot are down here, which, by the way, if you're missing a handout, no big deal. What I tend to do when we get close to the time of our first celebration, I'll pass around the notebook. I have a notebook where I've collected all of our handouts, and if you're missing something, you let me know, and then I'll have it to you, so you should have ample time to study it before the first exam. But real quickly, just to recap some of these ACI requirements. So before we get into that, one of the big things I want to make sure that you understand is this: the fact that, if you're given a beam, dimensions, area of steel, material properties, what have you, that you can take this information and compute MN, the nominal moment capacity, and that you understand the Whitney stress block model. That is very important. And if you don't understand that, please make sure you're asking questions. The stress block model, the 0.85 SC prime, the Whitney stress block. I'll call it the Whitney stress block every now and then, but the ACI stress assumption model, 0.85 FC prime for the width of that stress block, applied uniformly over a depth A, which equals beta 1 times C. Everybody okay with that? Okay. Then we went through this, but we really didn't employ it. So I'm going to take some time and go through this. These are the ACI requirements for RC beams. I'm going to go through it a little quicker than we did last time. But so to start off, we assume this nonlinear stress, or we have this nonlinear stress distribution for the concrete that we simplified with the Whitney stress block. But we didn't talk much about the strain. Remember, the strain profile, we assume that it's linear, that plane sections remain plane. We define that based off of the maximum usable strain in the concrete, which we assume to be a constant value of 0.003. As for the stress block, we define that depth A to be related to the neutral axis depth C by this constant beta 1. And beta 1 shrinks as the concrete gets stronger. The larger the compressive strength, the smaller beta 1. So you can think of it like this. The larger that beta 1 value is, the skinnier your stress block is. And that's basically what we've got going on here. Okay? So it's a linear fit between 4 KSI and 8 KSI, and constant anywhere after that or before that. We have a minimum steel requirement that basically says, I don't care that you're being strong enough or whatever, you are going to supply at least some minimum amount of steel in the beam to ensure that we don't have sudden failure, and that is calculated as follows, pretty straightforward. We have a linear strain profile, so if we know that the top of that strain profile is 0.003, we can calculate strain anywhere else in the beam using similar triangles and just slope ratios. Now, the one point I will make is, we do this right now to check whether or not the tensile steel is yielded. Because right now, we're dealing with beams that look like this. And all we care about right now is that the tensile steel has yielded and that strain is larger than 0.004. And that'll always be the case for a singly reinforced concrete beam. A doubly reinforced concrete beam, however, that might not be the case. A doubly reinforced concrete beam being one where we have rebar here and here, okay? Which we almost always have anyways, because when you build a rebar cage, you've got the rebar on the bottom, the rebar on the top, and the stirrups tying everything together. If you account for that rebar up top, you get benefit in long-term deflection performance, and also you have to account account for it when you're looking at columns anyways. The downside is that the analysis can be a little trickier because you actually have to determine whether or not that compression steel has yielded or not. But we'll get to that later. But all I'll say is this check becomes much more important when you're dealing with beams like that. Now, how do you determine whether or not that tensile steel is yielded? It's if that strain is larger than the yield strain. How do you calculate the yield strain? It's just Fy over Young's modulus. So for 60 grades or grade 60 steel, it's about 0.002. Now, ultimately, our limit, though, I don't care what the beam looks like, is that tensile steel has to be greater than or equal to that. And that's basically ACI's way of saying, I don't care what's going on, that tensile steel better yield. Okay. Now, the reason why that's important, we want a beam to be tension controlled. We want it to be governed by the behavior of the steel and not the behavior of the concrete. When steel yields, it's a pretty gradual process. You get large deflections. You know what's coming. If it's governed by the behavior of the concrete, when it goes quick. And we don't like that from a safety perspective. So in ACI, we define tension-controlled elements and compression-controlled elements. When you look at elements that are tension-controlled versus compression-controlled, you get different values of phi, your strength reduction factor. Remember, we calculated last time Mn, the nominal moment capacity. What we really are after, though, is a design moment capacity, a moment capacity adjusted by phi to account for uncertainties, to account for uniform levels of safety. Here's our model for phi in ACI for elements that are under bending or compression. So if you have a member that's predominantly undergoing compression, when it goes, it's going to go quick. So its phi value is pretty low, 0.65. If you have a member that's primarily controlled by the behavior of the steel and tension, then we've got gradual levels of failure, and we can up that phi value to 0.9. Anything in between, it's a linear trend based off of the strain that you're actually getting in the steel and the strain at yield. And how do you calculate the strain at yield? Right there. Everybody good? Okay. And this was just a note regarding multiple layers of steel. Not really big deal right now. Everybody good? Now what I want to do is I want to go back to this problem, and I want to take some of those limits one by one and kind of assess them accordingly. So this is going to be, we're going to go back to example 4, that same beam we were looking at earlier, and evaluate some of the ACI requirements. So now let's make sure that we're good on example 4 in general and that we know what's going on. All right? So example 4, we were given grade 60 reinforcement, so we know that the Fy is 60 KSI. We have 3 number 8 bars, so we know that the area of steel is 2.37 inches squared, just taking the area of a single number 8, multiplying it by 3. Okay? Here's our model for calculating the capacity of a reinforced concrete beam. We have a rectangular beam that's B wide. Its effective depth is D. From the top to the neutral axis is C. Now, this is what we're really going to get, a nonlinear stress distribution. We don't like dealing with nonlinear things. We like to keep it simple. So we assume a uniform stress distribution. The magnitude of that stress is 0.85 FC prime. The depth of that stress block is A. The relationship between A and C is defined by beta 1, right? Okay. Now, the tensile force in this section is just going to be the area of steel times Fy. Make sense? Now, that's assuming that the steel yields, which we will check. Okay? Area of steel times Fy. Okay? The compressive force is the same kind of deal, stress times area. The magnitude of that stress being 0.85 FC prime, the area being A times B. Remember, this is the area that we're looking at. The one quantity we do not know is the area, or not area, but A. We don't know A. So we solve for A by recognizing that the compressive forces must equal the tensile forces, get an A value of 4.182 inches. And then we calculate moments by just looking at it as if it's one simple force couple. A force, two opposite equal and opposite direction acting forces separated by a moment arm. It's just the force times that distance between them. So the force can either be C or T, right? It doesn't matter because they equal one another, times the moment arm. How far is it from these two forces? How far are they separated? It is the depth, the effective depth, minus A over 2. Does that make sense? So, excuse me. Plug and chug, and we get, incorporating units, we get a nominal moment capacity of about 245 foot kips. Everybody good? Okay, all right. Okay. Now, I'll say, let's just sort of continue with this problem, and I'll say, let's look at strains. Okay, so recall for this problem. A was about 4.182 inches, right? Now, what is beta 1 going to be? Now, I gave it to you for this problem, but we're going to make sure that we understand that. 0.85. And it is 0.85 because FC prime is 4 KSI, right? Again, make sure that we see where this is coming from. Here's our relationship for beta 1. Beta 1 is 0.85 anytime FC prime is 4 KSI or less. Linear fit off of that until we get to 8 KSI. Everybody see that? Okay. All right. So my point is, if we know that A is calculated as beta 1 times C, what can we calculate? C. So C is A over beta 1, which is 4.182 inches over 0.85, which equals 4.92. So Lee, you asked this question earlier, how are we, where does beta 1 matter? We don't use it to calculate A as much as we actually back calculate C. All right. Everybody okay with this? So far, so good. Now, let's also make sure we understand what's going on with the problem in general. Keep in mind, here's our beam. We have steel, steel, steel. Doesn't matter how many bars. We have a beam that is B wide, and that beam has an effective depth of D, okay? Now we can say this is the area of steel, although we really don't care about that right now. Now, let's do that about right there. So this is my neutral axis, okay? Now from the top, from here to here, we have a term for that. What do we call that? C. That's C. That's not A, that's C, okay? So, pop quiz. How far is it from here to here? There we go, D minus C. Not too bad, right? Okay. Now, what does the strain profile look like? That's what we're talking about now. We're talking about the strains. Now, the stress profile, we know we have, this rectangular block up here and so on and so forth. But remember, strain, plane sections remain plane. And we assume a linear strain profile. So it looks something like this. So if you want to, I guess, a more analytical definition of the difference between A and C, A is the depth of your stress block. C is where the strain equals 0. Now, pop quiz. What is the magnitude of strain at the top of this section? Right here. How much is that? There we go. We always assume a maximum usable strain of 0.003. What I am after right now is the strain right there. And I'm going to call that epsilon sub t, the tensile strain. Okay? So watch how I'm going to express that. So everybody watch this up here. Would you agree that the ratio of this to this is the same as this to that? It's straight lines, you know, just slope ratios. So 0.003 is to C as epsilon sub t is to D minus C. You okay with that? So, can I calculate the strain in the steel as 0.003 D minus C over C? See how I did that? Just take that, multiply it over. So that is 0.003. What is D? You tell me. 23 inches minus 4.920 4.920. I'm going to have to copy that on the next screen. I'll give you all a minute to write that down. No. Let's see. Yeah. No, that's fine. That's fine. Yeah. I'll give you all a minute. All right. Everybody good so far? Okay. All right. What I'm going to do is I'm actually going to copy all this. Okay, so if we plug and chug, we're going to get a value of about 0.0110. Is everybody else getting that? Okay, all right. Let's make a couple points, okay? How do we calculate the strain at yield? It is Fy times Young's modulus, right? What is Fy for this steel? It's grade 60 steel, 60 KSI, right? I'm lazy. I don't want to write 3 more zeros. What is E? So if I plug and chug, I get about 0.00207. So keep in mind, when we did our problem, we assumed that the steel would reach its yield stress. Was that a valid assumption? Yeah, oh yeah, it was. We're comparing a strain of 0.0110 to a yield strain of 0.0021. So did it yield? Oh yeah, it yielded. It really yielded. So that was a very valid assumption. Okay, so I want to make a few points about this. Okay, so I'll say points to make. And I got 3 big ones. 1, assumption that the steel yielded was valid. That's a good question. We assumed that when we assumed that this force was the area times Fy. Keep in mind, this is our stress distribution, and we assumed, we're talking about ultimate loads, and we assumed that the strains would be large enough such that this would reach Fy. Because we said the tensile force was As times Fy. So we're assuming that it reaches yield. Does that make sense? That's a good question. That'll be different for a doubly reinforced beam. But yes. Yes. Okay. So the assumption that the steel yielded was valid. Okay. Number 2, what is our ACI requirement for strains? The ACI requirement that epsilon sub t must be greater than or equal to 0.004. Was that met or not? Oh yeah. Now, let's see if you all can see where I'm going with this. The tensile strain is larger than 0.005. Therefore what? What does that mean? Why do we care about that? That it is larger than 0.005. I'm going to make y'all search for this one. Okay, keep going. So how about this? It will. Okay, you're right. All right, so I'm going to say, therefore, the beam. Oh, goodness. Thought I had. Oh. The beam is tension controlled. And phi is 0.9. Does everybody see that? So we got a lot of information from that strain in the steel. We know that the steel had yielded, it met ACI requirements, and that told us that phi was 0.9. Is everybody okay with that? So therefore, what is phi mn? It's 0.90 times what? There we go, 247.8 foot kits. Phi mn is That is the member's design capacity. That's a very important point to make. Yes, sir. All right. I'll bring this back up. Yes. Yeah. Yeah, I should probably move that here. This is what I'll do. I'll take this and maybe put it like here, then do, that's probably a little clear. Sorry about that. That's a fair point. Yes, sir. That's its design capacity. Here. Can I move off this? All right. That's its design capacity. Remember, MN is the nominal capacity. Phi MN is its design capacity. With the strength resistance factor applied to it. Everybody seeing this? Okay. Everybody good? There's one last thing I want to check, and that's whether or not we've met the minimum steel requirement for this problem. So I'm going to go on to another slide. Is everybody okay? All right. Okay, our minimum steel requirement says that the minimum steel that we must provide is equal to BW D over FY times the maximum of 3 times the square root of FC prime, or 200 PSI. That's just our model that ACI applies. It's not bad. I'm going to start off by evaluating 3 square root of FC prime. Okay, so 3 square root of FC prime is 3 times the square root of what? Yes. What is FC prime for this problem? Exactly. The big thing. You plug in PSI, you get out PSI. So 3 times the square root of 4,000 comes out to be about 189.7 PSI. So which one are we going to use, that or the 200? The 200. So therefore, AS minimum is, now B sub W, that's just the beam width, okay? So that's going to be 10 inches. D is 23 inches. Then we have times the maximum of those two, which is 200 PSI. And then what's FY? There you go. Units. This is 60,000 PSI. Now, if you plug and chug these numbers, you're going to get 0.77. What are the units going to be? The PSIs are going to cancel, and you're going to be left with square inches. Now, how much steel do we actually have in this beam? What is, so I'll say, for this beam, there you go. For this beam, area of steel is 2.37 inches squared. Therefore, minimum steel requirement met.
So that's not, the AS then is not per, we, it's 3 times 0.79. Is AS
No, it's for the beam. For the beam. Not saying each bar must be. No, that's a good question. No, it's just saying that the beam must have this much steel. Think about it like this. Let's say, okay, this beam has what, like 2.4 square inches of steel, right? We met that requirement, or that limit is met by having 3 number 8s. What if you put 4 number 7s?
What number 8 would that?
Well, yeah. Okay. But what I'm saying is later on, what we're going to be after is ensuring that we have enough steel for strength, and there's going to be multiple different ways that we can do that. And there are beam charts we're going to look at later on.
So, like, this might sound stupid, but like, if the actual, like, if the AS actually was like 0.78, it would still be it.
Yeah.
Okay. So it's anything that's above that.
Yes. Yes. I will say this, it's rare that this actually becomes an issue, but you still need to check it. All right. Everybody good? Anybody have any questions? Okay. Okay, we got plenty of time. Okay, I'm going to leave this up here for a second. And in the meantime, I'm going to hand this out. We'll spend this slideshow I'm handing you all out right now will last us for a little while. I didn't say that. Always looking for the positives, aren't we? All right. Has everybody got this? Okay. What I'm going to do is, it's going to be a little bit of story time, what comes next. I mean, I'm going to be lecturing, it's going to be a lot of like equation back and forth and what have you. I promise you I'm not really expecting you to do a lot of these derivations that I'm about to show you. It's really what you're seeing now, or what you're going to see in these upcoming slides, is for discussion purposes so that you see where our procedure for design comes from, okay? Because, we had this discussion last time in steel design. What we did just now is assess, given a beam, how strong it is. Now what we're going to do is say, based on a span length, based on some loads, how do we size that beam, okay? And we're going to do this 2 different ways. We're going to look at it from 2 different point of views. One of them, we're going to ask ourselves, how do we design the beam if we don't even know what the cross-section looks like? The other method is, what if we do know what the cross-section looks like? A lot of times in concrete design, you're using very typical standard molds, and the only question we need to answer is how much reinforcement needs to go inside those molds. So there's 2 different methodologies we need to assess, so we're going to do both of them back to back. Before we do that, though, I want to discuss a little bit about economy in reinforced concrete beams, because I think there might be a tendency right now for those of you, thinking about concrete design, thinking about how this stuff works is, well, how do you make, if you have a beam, how do you make it stronger? Throw more rebar in it, And that's not always the right answer, because there is such a thing as throwing too much rebar in it, okay? And there's a balancing act that you need to perform. Another interesting, or I guess terminology I'm going to throw at you right now is I'm going to throw this term at you right here. This term, a reinforcement ratio. We're going to use our resistance factor and our reinforcement ratio to have a little bit of a discussion about economy. Okay? Now, let's talk about reinforcement ratios. A reinforcement ratio is defined as, I guess the easiest way to say it is the area of steel divided by what I'll call the effective area of concrete. So the area of steel divided by the width of the beam times the effective depth of the beam. And it's kind of a measure of about how much steel there is in a beam. The larger that number, the more percentage of steel there is in that beam. Make sense? So would a fair statement be that I can express the area of steel as BD times this new term, this reinforcement ratio? We'll call it rho. Yes? we'll get to stuff like that later. To answer your question, that's a good question about box beams. Box beams are going to be treated more like T-beams because it's really not much different, because what you're really talking about more is more about the analysis of a flanged section, because you have a really large flange and then a web. Okay? Now, what's the difference between a T-beam and a box beam? From a capacity calculation standpoint, really nothing. We'll get to that, though. We've got to walk before we can run. We've got to crawl before we can walk. And I want to have a little bit of a discussion about walking and crawling first. We'll get there. I promise we'll get there. All right. Everybody okay with this? Okay. Now, let's go back and make sure we understand our philosophy. So, how did we calculate this A value? We said 0.85 FC prime AB equals ASFY. The tensile force equals the compressive force. And then we solved for how much depth was required in our stress block such that C equals T. Everybody okay with that? Okay, now what I want to do is I want to substitute this new reinforcement ratio term that I brought up earlier. Everybody okay with that? So, see, I've got this sort of made blue, this area of steel, and then I'm saying rho BD. Just substitute it in. Now you look at this fraction, what happens to the B's? They cancel out. So the area, or the depth of the stress block A, instead of saying this, I can say this. Is everybody okay with that? Everybody good? All right. Now, how do we calculate moment capacity? It's ASFY times D minus A over 2. Everybody okay with that? So I'm going to do similar substitutions, okay? Now, the area of steel, I'm going to say is rho BD, and my stress block, I'm going to say is this. So ASFY D minus A over 2. The AS becomes this fraction A over 2. See how it's over 0.85? So I get the 1.72 times 0.85. Everybody see that? I'm just substituting it in. Now, how do I get from here to here? I just factor out common terms and simplify it a little bit. Is everybody okay with this? I know it's a little bit of algebra, but bear with me. Everybody okay? Okay. So what I've got here, and I really want to make sure that we understand what we see here, I've got an equation that expresses the moment capacity as a function of this term BD squared and some material properties. So if I divide that over, see how I've got this? This term here, this MN over BD squared, is sort of a nominal expression of capacity. It's kind of a measure, if you will, of the effectiveness of that beam. Now, there's a point I'm going to make here in a second. What you see here on the right is a plot of this curve. Now, I've just assumed 4 KSI concrete and 60 KSI steel, very common material parameters. So, right off the bat, it looks like, okay, look what's happening here. The reinforcement ratio is getting larger. So what it looks like is that for a given beam, as I throw more steel into it, it gets stronger. Seems to make sense, right? But this is MN, okay? I don't care about MN. I care about phi MN, okay? So what happens if you start to adjust these values by phi, by their strength reduction factor? What happens is, see how you've got 3 regions of beam behavior according to ACI? You end up getting 3 regions of behavior when we're looking at factored resistance. What happens is, this region right here, this is the tensile controlled region, the tension controlled, because we're not talking about a lot of steel, so the steel that is in the beam is experiencing very, very large strains. But when we start piling steel into that beam, like we say, okay, we got to really throw a lot of reinforcement in there, that steel cannot experience those large strains, so the beam starts to become more controlled by compression. So one of the points I want to make is it's not always, it's not always as simple as, well, I'll just throw more steel into it and that'll make it stronger. Yeah, you might make it stronger from a nominal standpoint. You're not making it safer. That's a different question, okay? And that's what phi tries to answer. Okay? Does that make sense? Now, we're designers. If we wanted to design, what do you think we want phi to be? Let me ask it in a different way. Do we want beams to be tensile controlled or compression controlled? If we wanted to dictate beam behavior, what would we want? Tension control. So we want phi to be 0.9, which is really what's being expressed in this range here. Okay? We're going to use that assumption later on. All right. Now, let's just keep that in mind. Now, I want to go back to this. Would you agree that I can take this expression, rearrange it a little bit, it's just alphabet soup and algebra, and I can solve for BD squared? Do you agree with that? Okay. You look at this and sort of, conceptualize it in your head a little bit. What is in that box? Well, we have BD squared is equal to this term in the brackets, which is just a function of material characteristics. We can assume an FC prime and an Fy right at the beginning of the problem. And the only thing that we really need is a required moment, which we can get from what the beam is experiencing, and a rho value. Now, excuse me. Everybody good so far? Okay. These rho values, these reinforcement ratios are really nice because they can serve to, they help us determine what the economics of a section are, and they can also be pretty useful for design. We're going to use a design rho value in this course that I will show you here in a little bit. Maybe I'll just go off of this next slide and just show you. Right now, we are using ACI 318.14, which means it's the code that came out in 2014. ACI is on a 3-year code cycle, and every 3 years they come out with a new edition of the spec. Now, some things don't change, like 0.85 FC prime, the Whitney stress block approach. That isn't going to change. That's been there for decades. It's not going anywhere anytime soon. But some things do change. Things like reinforcement ratio requirements and things like that, they have changed here and there throughout editions of the spec. Now, there was an edition of the spec a while back that included a reinforcement ratio limit that you would use for deflection checks. And those engineers that had a fair amount of experience with the spec, what they'll tell you is that value is actually pretty useful for design. Okay? We can use this value to kind of get an idea how much reinforcement we should put in the beam for the purposes of design. And we're going to use that for design in this course. Okay? Now, how's that going to come into play? Let's go back to this. Okay? This is our strain profile. See how I came up with this? This whole 0.003 is to C as this term is to that. Y'all remember that? Okay, I'm going to solve for this ratio. You all agree with what I have here on the slide. This should be little more than algebra and alphabet soup. Plug and chug. Everybody okay with this? Okay. I'm going to use that and substitute this, this expression that we have for A. I'm going to use that, and bear with me for a little bit. You'll see where this is going here in a little bit. I'm going to use that and plug in for this C over D to kind of get these two different expressions, if you will, for this ratio. So one of them is based off the strains. One of them is based off equilibrium. Okay? Everybody all right? The nice thing about that is that these two have to be equal to one another. Excuse me. Everybody good? We're getting somewhere with this. I know that I'm throwing some equations and a lot of terms at you. I know where you're going, oh goodness, what the heck's going on here? You'll see where this is going very shortly. Okay? So what I've basically defined for you, if you look at this term for a reinforcement ratio, I mean, take a little bit of time and pay attention to this. I've got this reinforcement ratio as a function of material properties and target strain in the steel. The nice thing about this is that we can use this expression for beam design. Okay? Let me show you how this works. Okay? And we'll take our time and discuss this, and I think you'll see, oh, I'm kind of seeing where we're going with this. Okay, so what I have outlined for you right off the bat is a procedure for design, assuming that we don't have a freaking clue what the beam looks like in any way, shape, or form. We don't know how much steel is going to be in the beam. We don't know the dimensions of the beam. We don't know anything. Okay, so the first thing that we're going to do is we're going to compute the moments that are on that beam. Okay, now, what load must all beams be able to withstand? Their own self-weight. We don't know what the self-weight is. We have to determine something. So notice here, and I've got this in big, red, bold, underlined values, we need to assume what the self-weight of the beam is. Okay? So I'll just go ahead and say it. With more experience in concrete design, given a different span, you'll do better at this. After time, you'll learn, okay, this beam's 30 foot long. It should weigh about this much. You'll be able to assume this value a little better. Okay? Yep. Am I running out of time? Nope. I got a little bit of time. Okay. Based on a given span arrangement, you will be able to assume beam weights the more you do this. For now, this is your first time. Okay? So what I will do is provide you this sort of guide. This is minimum beam heights that ACI stipulates for deflection purposes, and we'll use that to define about what the beam self-weight is going to be. Once we get the beam self-weight, we can compute the factored moments, 1.2 times the dead plus 1.6 times the live. Everybody okay? What we're going to do with that is we're going to have a factored moment. Based off that factored moment, we're going to compute what's our required MN. To do that, we're going to assume a phi of 0.9. Everybody okay? So far, so good. Off to the side, we're going to compute what's a reinforcement ratio we can use for design. That's a really simple one. That does not have to be the one that you start with, but this is a nice one for design. It works pretty well. Okay? So we've got a required MN, and we've got a design value that we can use for our reinforcement ratio. Based off that required MN and reinforcement ratio, we can compute this. Now this is important because look at what we're computing. We're computing a required BD squared. Now we're starting to get a picture of what the beam looks like. Because what is this? BD squared. Those are the dimensions of the beam, right? Make sense? Now we're starting to get an idea. All right? Now we might say the beam needs to be twice as deep as it is wide. Based on that, we can get, well, how wide's the beam? How deep's the beam? That's a pretty good assumption. Now we've got a beam width, and we've got a depth. Now we've got what the beam looks like. Okay? Based on that, we can compute what the required area of steel is. Pick a pattern of steel to go into the beam. Well, dang, now we've got a beam design. Based on that beam design, we then need to go through and analyze it because we've got two assumptions we got to verify. We've got to verify that phi is, in fact, 0.9. We've got to go back and check how heavy our beam is. And I can almost guarantee you, doing it this method, your beam will come out heavier. I know this was a lot of information to throw at you. We will take this step by step next time. Now, there's a couple of additional beam requirements, like how many bars you can put in a beam for spacing and things like that, and temperature and what have you. We'll get into that next time. But next time, what we are going to do is actually begin the process of beam design. Before you leave, I have a take-home present for you. Oh, I know. I can hear it now. Woe is me. Well, it was going to be on MU Online anyway. So this is due in 1 week, due on Monday. It looks like there's a lot of problems. One of the problems, or some of the problems are actually kind of short, so be prepared for that. There is, hey, one thing I will say, I've got one on there that is kind of funky. I have a triangular beam on there, so if you understand this stress block concept, then you should be able to determine what the capacity of that beam is. I will have it posted on MU Online.
I don't have internet access.
You have it on campus. All right, guys, I will see you all next time.